Hello everyone, my name is Mary Stackrook and I'm a student at St. Mary's University in Halifax. I'm part of the Brousseau group and I'm very excited to be presenting to you my undergraduate research. Copper screen-printed electrode substrates for copper-based electrochemical surface-enhanced Raman spectroscopy sensing, ECSURS for short. So the Brousseau group has particular interest in the field of plasmonics, which is essentially the scattering of monochromatic light. This is when electrons in metal nanospheres or metal interact with light, and the collective oscillation of the electrons are plasmons. And because they are in a uniform motion, we call them localized surface plasmon resonance. Now, how do plasmons scatter? We can divide them into two categories, Rayleigh scattering and Raman scattering. Rayleigh scattering is the elastic scattering of monochromatic light. Meanwhile, Raman scattering is the inelastic scattering of monochromatic light. Now we can divide Raman scattering into two other categories, Stokes and anti-Stokes. Anti-Stokes is when the incident photon has less energy than the scattered photon, and Stokes is when the incident photon has more energy than the scattered photon. Overall, this energy difference between the incident and scattered photons we call the Raman shift. However, only 1 out of 10 to the 6 photons are inelastically scattered. So this is something to consider when we take a look at SIRS and ECSIRS. Surface-enhanced Raman spectroscopy surface coatings are commonly silver, copper, and gold. And the reason for this is that they are capable of supporting surface plasmons. As you can see on the graph, on the y-axis we have quality factor, and on the x we have wavelength. Now the strength of the surface plasmon is represented through this quality factor. A large Q indicates strong plasmons, meanwhile a small Q value indicates loosely or weak surface plasmons. Ideally, we're looking for a Q value that is larger than 10. As you can see, silver has the best quality factor across the largest spectrum of light, 300 to 1200 nanometers. Meanwhile, copper and gold have limited LSPR excitation wavelengths, unlike silver, only from 500 to 600 nanometers. Now, what is an ideal SIRS substrate? It is essentially something with nanoscale roughness and has a uniform template. Now, a carbon screen-printed electrode fits perfectly in these categories. As we use our scanning electron microscope, SEM, we are able to zoom in onto the carbon screen-printed electrode and notice that it certainly does have nanoscale roughness that would be a perfect candidate to have metal nanoparticles or nanospheres deposited onto it. Therefore, the carbon screen-printed electrode would make an excellent SIRS substrate. So SIRS and plasmons. As I mentioned earlier, we use a coinage metal that is capable of supporting plasmons. So we can deposit some sort of metal onto our carbon screen-printed electrode, and we can use our monochromatic light and form these regions of high energy and high enhancement for our molecule. And we call these hotspots. Here, when we use a coinage metal, we are able to have 1 in 1 photons are inelastically scattered, compared to regular SIRS, when 1 out of 10 to the 6 photons are inelastically scattered. This is a much more enhanced technique. However, we can take this enhancement even further with electrochemical surface-enhanced Raman spectroscopy. Here, we can take a low concentration of a molecule and have great signal molecule detection. Once again, we can use this carbon screen-printed electrode, and we apply a voltage, as well as using our monochromatic light, and we can draw the analyte to the surface. And with this, we have 10 to the 6 and 10 to the 7 enhancement factor, which is quite significant compared to regular Raman scattering. So I spoke about earlier a few types of metals that we can use. Copper, gold, silver. But in this research, I was quite interested in copper because the current cost of silver is currently 90 cents a gram, and the abundance in the Earth's crust is only 7.9 times 10 to the negative 6%. Meanwhile, the cost of copper is nearly $0.0043 a gram, and the abundance of copper is 0.0068%, which is much more than silver in the Earth's crust. And once again, copper has similar plasmonic abilities and still a high quality factor. So why not use copper as our coinage metal for SIRS or ECSIRS? It does have its disadvantages, unfortunately. Copper can suffer oxidation, has limited LSPR excitation wavelengths from 500 to 600 nanometers, and poor stability as well. So how can we attack these consequences, these problems? We can use something called physical vapor deposition, which essentially is thermal evaporation, and here we can produce up to 4 substrates during each deposition. So I can coat 3 or 4 screen printed electrodes with a copper film, and it can efficiently be done in under an hour. So the way the physical vapor deposition works is it evaporates copper pellets or copper and sends it through a condensed phase. Finally, it is transported through a gas phase and condensed through a gas phase, and finally finishes and condenses onto my screen printed electrode. So it is quite efficient, and once again, I no longer have this issue of poor stability. Here we see a copper-coated carbon screen printed electrode. As you can see, the PVD has done a beautiful job in forming a uniform collection of nanospheres at 80 nanometers in diameter, perfectly capable of supporting plasmons for EC, SIRS, and SIRS analysis. I wanted to see how long it would take for the copper to oxidize on my PVD-coated copper screen-printed electrodes. I did this analysis through SIRS. First, I deposited a copper screen-printed electrode, and then I deposited my PYOT as my analyte. I next performed SIRS, and I did so for an electrode that was 2 and 3 days old. As you can see, the enhancement decreased after 1 day, which that leads me to say that the copper-coated screen-printed electrodes can only be used for 1 day when performing SIRS. I was so determined that copper could work for some sort of SIRS analysis, so I reflected on a previously published paper when we used silver as a coinage metal for EC SIRS analysis, and it worked perfectly. So I thought more about this, and I figured that I would use copper as my coinage metal for EC SIRS analysis. But before then, I wanted to make sure I have a few bases for the analytes that I was interested in. Adenine is a DNA aptamer, so I was quite excited to see this as it's all in us. So I took a look at adenine and I recognized these significant peaks, and I was able to transform this and create it in a electrolyte solution with adenine and use this for my EC SIRS analysis. And I was able to see adenine, and I was overjoyed. As we step further negative, the adenine peaks become significantly more prominent. So I was so excited. So the next question I asked myself is, how long could I use these screen printed electrodes for EC SIRS sensing if SIRS sensing I can only use for 1 day? So I used my adenine in electrolyte solution on a few aged electrodes, day 1 through day 15, and look what I saw. I was able to see similar enhancement, if not the exact same enhancement, of adenine on a screen printed electrode up to 15 days. This copper lasted 15 days, and I was overjoyed. So I said, okay, maybe one more analyte we'll take a look at. I looked at levofloxacin, which is an antibiotic. I was familiar with a few of the peaks and what I should be looking for, as well as the vibrational modes, and I made levofloxacin in a sodium fluoride solution. And once again, I used it on an electrode, but I wanted to start much later. I wanted to see, maybe I'll just start it on day 11, on an electrode that was 11 days old. And once again, I was able to see levofloxacin, and I was overjoyed. This electrode, I can see 2 different analytes, and the electrode can be used up to 15 days with copper coating on it. This is fantastic. I had to know why. So I said to myself, I wonder why this is. So I took an electrode, a copper-based electrode, and I oxidized it through bulk electrolysis, and then I decided to run a cathodic sweep. And I was able to see that the percent of copper oxide decreased after performing 1 sweep of bulk electrolysis. So that just goes to show that the reason why we are able to see enhancement of our analyte on an electrode that is so old is because the bulk electrolysis is able to reduce the oxide layer, which couldn't be done in CERS because we don't use a potential. So I was so excited, and I only wanted more. So what's next in this research? Essentially, I want to optimize the copper screen printed electrode's ability to be reused. I want further exploration of other analytes, other than adenine or levofloxacin. And finally, I want to be able to figure out how to stop the oxidation of the copper-based CERS substrate so I can use my CUSPE for CERS sensing. So before wrapping things up, I want to give a few shout-outs and some huge thank yous to my supervisor, Dr. Krista Brousseau, Dr. Sean Yang, the technician for the SEM, Alyssa Dewey, Dr. Najwan, Dr. B2, and Dr. Elizabeth McLeod. And of course, the entire SMU Chemistry Department, the entire Brousseau Group, the Canada Research Chairs, the NRC, and the Canada Foundation for Innovation. Thank you. Finally, I want to thank everybody for listening, and if anyone has any questions, I'm here. Thank you very much, everyone.